with that, I would like to move to the next presentation to be given by my friend and colleague, Adrian Chong from the National University of Singapore. And now I'll start using to get to some of the tools that characterize a digital transformation, naming the tool of the digital twin and how it applies to buildings. So Adrian, the floor is yours.
Thanks, Kostas. So good morning, good afternoon, and good evening, whichever time it is where you are. So first of all, thanks, Kostas, for organizing this workshop and providing the opportunity for me to share the work from my research group. So today, the topic of my presentation is on the digital twins of buildings and exactly how much information do we need to meet the purpose that we actually built these models for. So with data in the built environment becoming increasingly available due to the rapid deployment of smart energy meters as well as IoT devices, so we are seeing more and more promises of an energy digital twin of buildings, as well as the benefits that it will be able to bring to support the decisions needed to uncover significant energy savings in the built environment. So although there have been many talks about all these potential benefits, what a digital twin of a building would bring, what is less clear in my view is the modeling effort as well as the data requirements of such a virtual representation of a building. So specifically, there seems to be a sense that more is always better when it comes to digital twins. So hopefully during this sharing session, I'll be able I will discuss the creation of these energy digital twins of buildings, and more specifically some of the ongoing work I have at my research group on the level of information and the model calibration effort that is needed to meet the promises that all these models are supposed to bring. So these images are probably not unfamiliar with most of you. So over the past 5 years, there have been many demonstrations of digital twins. So these include dashboards showing real-time building energy consumption, as well as very detailed 3D model. So for instance, on the top left, we have something, a display of building consumption over time. And then in the middle, we see a time series plot of, temperature and humidity, and many times, from all these indoor air quality devices, like what Stefano showed, you will also see, like your CO2 and your PM 2.5. And then on the right is, is another typical time series plot of PV production. So at the bottom, what we have, what I'm showing here is a 3D model of the recent net zero energy building located on the National University of Singapore. So the big question is, would you consider all this to be digital twins? Or rather, the more appropriate question is, under what use case can this be considered as digital twins? So in my view, a digital twin refers to a virtual representation or information construct of a physical system. And the intent of the digital twin is so that it could be used to provide information that would be impractical or often impossible to obtain with the actual physical system. So often, when the building is operating, you can't just go in and change things. You can't switch out a glass and change and see how that performs. So the increasing data availability in buildings, in my view, should be used to also increase the credibility of the model. So we can then use the model and work in the virtual space to simulate various scenarios that translate into information that can help improve building performance. So I'll be focusing more on building energy models because that is where my research interest lies. So I show a few logos on the right. So widely used energy modeling software includes white box models such as Energy Plus and Transys. And as well as, in the realm of model predictive controls, the resistance capacitance models is also often used. So in the context of creating building energy digital twins, use cases that we often think about could include, trying to simulate an experiment without knowledge of its results, such as retrofit analysis, you're trying to compare the cost effectiveness of different energy conservation measures. It can also be used to understand, phenomena that cannot be studied experimentally, such as the impact of climate change on building energy performance, and how we can design or retrofit buildings so that they are robust towards climate change. And we can also use these energy digital twins to extrapolate our understanding of the building's energy performance beyond existing operational regimes, because typically a building operates within a very narrow range of operating conditions. And this model can then be useful in applications such as optimizing building controls, as well as measurement and verification. So additionally, I believe that a digital twin should be linked with its physical counterpart throughout its building life cycle. So in the case of a building energy digital twin, the first model of the building typically would be from the design stage, concept design, where energy model has been widely used to support decision making, by informing the trade-offs between cost, energy, and more generally building performance. So the reason I say this is because, creating a model is a time-consuming and often labor-intensive process. And which is why I think it would be such a waste if the model is just discarded after the design phase, despite the potential users that we see in the later phases of the building life cycle. Therefore, there is also increasing efforts towards using this model after the design phase. So this includes updating the model during the construction phase and subsequently using it during operations and controls through continuous calibration. So however, as building energy simulation becomes increasingly used throughout a building's life cycle, there are also increasing concern about the model's credibility as significant discrepancies between simulated and measured energy use becomes more apparent. Especially, with the rapid deployment of smart energy meters, people start to see, oh, your model is so different from what we are actually measuring. So what we see in this figure is a well-known study of 121 LEED certified buildings. And the authors found that, the ratio of actual to predicted energy use, there is significant variance even within the same LEED certification levels. And specifically, they showed that, measured energy use can be somewhere between, 0.5 to around 2.7 times the predicted energy use. So what are the potential causes of these discrepancies? Previous research have observed that the main causes of discrepancy between predicted and actual energy performance can come from specification uncertainty. So this arises from assumptions due to a lack of information. So the typical workflow is that if I do not have the information, I would go back to the standards or the guidelines. So I would use the default values in the simulation tool. So another possible cause of discrepancy is model inadequacy that arises from simplifications and abstractions of the actual physical system. And there is also operational uncertainty arising from a lack of feedback regarding actual use and the operation of buildings. So for instance, during design phase, there are certain assumptions made regarding, let's say, the supply air temperature. It could be 13 degrees Celsius as well as, the fresh air supply. But in actual operation, that might not be what was assumed during the design phase, or it could have changed during operation to suit the current needs of the building. And lastly, we have scenario uncertainty arising from specifying the model conditions such as your weather as well as building occupancy. So consequently, model calibration is typically undertaken to match simulation prediction to actual observation better and to increase the model credibility for making prediction. So calibration is the process, where we try to adjust the numerical parameters in the computation model for the purpose of improving the agreement with experimental data. So this graphic summarizes a recent systematic review of energy simulation calibration in the recent 6 years. And we can see from this image that, local weather data are often considered, which is not surprising since this form the boundary conditions of the model. And what is often used to calibrate the model includes, data such as your monthly electricity energy, as well as your hourly indoor air temperature. And lastly, parameters that are often calibrated includes, the thermophysical properties on the envelope. So these are things like your U values of your wall and your windows, infiltration rate, which is known to be very uncertain, as well as your internal gains that stem from things like your occupancy, lighting power, as well as your plug loads. However, after this review, and over the past 1 year, I have been thinking, I've been working on calibration for quite some time. And we spent lots of effort creating and subsequently calibrating all this energy simulation model so that they could accurately track, the output of interest, the output that we're interested in, such as, building energy consumption as well as indoor temperature. However, do digital twins really need to be complex models? Simpler models are more transparent and require less data for parameter estimation. In contrast, complex models are designed to represent the actual physical system better, but they tend to be more data intensive and, of course, also computationally more intensive. Additionally, I was also wondering if these digital twin models need to even be calibrated. So far, calibration has been undertaken with the aim of trying to improve the model's accuracy. However, what we require out of a digital twin, in my view, is credibility. So from a modeling standpoint, and depending on its use case, I believe that a credible model might not need to have high absolute accuracy, or it need not be a high fidelity model. Therefore, the crux of the issue is instead, in my view, to determine if the model is acceptable for what you're going to use it for, and exactly how confident we should be about the inferences that the model is telling me about its physical counterpart. So this brings the big question, exactly how much information do we really need? So with IoT and more data stream, as I mentioned earlier, creating a detailed high fidelity energy model has also become far from trivial. So now, besides spending time modeling the geometry and the HVAC system, having access to data, as Stefano previously mentioned, also now entails other challenges, pre-processing, data accessibility, and you need to ensure data quality. So this slide, what it shows is, the original, the level of detailed definition that is commonly used in the discipline of building information modeling. So basically, LD, or level of detail, is used to define the amount of building information that needs to be included in a BIM model. So the same concept can be utilized for building energy models. However, when creating a digital twin of buildings, and as the building becomes operational, additional level of details can be used. And they include data from phases like commissioning. And we could also use historical operational data. And if you want even real-time data to continuously update the model. Furthermore, there is an added dimension to all this, which is you need to consider at what spatial and temporal resolution do you want to have these data streams in. So this makes the creation of the digital twin even more complicated. And the main question that I have in mind is, do we really need all this additional information at the highest level of detail and at the highest temporal and spatial resolution for our digital twin to serve the purpose that it is designed for or built for? Is more always better? So in our attempt to answer this question, we need to zoom into specific use case, since the type, the granularity, and the amount of information required in a digital twin are typically driven by use cases. The first is the application of model predictive control and the effects that varying model complexity might have on control performance. And the second, research that I'm going to share is, on retrofit analysis, and the effects that different levels of calibration would have on the choice of design options, as well as the model's predictive accuracy. So it is this trade-off between, going after high model accuracy versus, as long as the model is making the right decision, that is good enough. So in the model predictive or MPC control study, what we are trying to understand is the impact that varying model complexity would have on the model's prediction, as well as the control performance. So what we see here, we are trying to investigate 3 different levels of model complexity using RC models, or resistance capacitance models, going from a R1C1 to a R3C2 to a R5C3. So the figure on the left shows the framework used for implementing the MPC. So we create a high fidelity model So this is the high fidelity model is created using the Modelica buildings library. And we use this to emulate a real building. So we are using an emulator because it allows us to comprehensively test various combination of model input and complexities under idealized situations, so we know what is happening within the model. So the generated synthetic data is then used to train the RC model that we also evaluate with a separate test data set. And then the control action is determined through optimization that is based on the identified RC model. We then apply this control action back to the emulator to look at how it is the control is how the control action is performing. So for better generality, we also look at another test cases. We look at 2 test cases, and they include a single zone office as well as a single zone classroom. So to more realistically, introduce variations in internal gains and external disturbances, the internal gains were modeled after actual occupancy data and plug loads data. So we actually measured data in an office space as well as a classroom over a 3 months period. And we use this as input to the emulator to try to emulate more realistically all this, the internal gains disturbances. And then we use actual weather data from a local weather station for the external disturbances. So this figure shows the root mean square error, illustrating the predictive performance, the prediction performance for the RC models across various complexities. So you see on this axis, you have the R1C1 all the way to the R5C3. And the other axis, basically, these are the inputs to the RC models. Basically, none refers to no input. So these are internal gains related inputs. So none refers to no inputs. Schedule refers to the use of standard internal gains profile. So these are the standard profiles that we typically use when we have, from your references that we use when we have no data. And electric ELEC refers to the use of plug load submetering data. And CO2 is the zone CO2 levels. And both refers to the use of both CO2 as well as plug load submetering. And lastly, the ideal case. So in the ideal case measurement, what we are using is actually the internal gains data that is obtained from the emulator. So in general, what we observe is that models with higher complexity achieve a lower root mean square error, especially for the training data set. But there is negligible difference between the R3C2 as well as the R5C3. So what we can see here is that, in the office case, the root mean square error was generally kept below 0.5 degrees Celsius when either a R3C2 or, a R5C3 model was used. In addition, it can be seen that, including various types of input data to the RC model does not improve its predictive performance when we are looking at the more complex R3C2 versus R5C3 model. In contrast, for the classroom, root mean square error was overall larger, and they generally exceeded 1 degree Celsius, which is quite a big margin for the more complex models, even for the more complex models. And we also observe that, including plug load data or both plug load and CO2 data led to better predictive performance across all models. What is interesting though is that if you look at the ideal measurement case for the classroom case over here, we actually observe a slightly higher root mean square error as compared to using other data streams. So this is because with the ideal measurement, the RC model actually has a lower degree of freedom. So this is we know exactly what it is, so we pass it as input. So the model actually has less parameters to tune. And we realized that led to a model with a slightly higher RMSE, like root mean square error, than its counterpart that has that additional parameter to be tuned. So this figure on the top left summarizes the control performance. So at a glance, right, what we observe is that, your R3C2 as well as your R5C3 models have very similar performance. We are seeing energy savings compared to baseline of around 10 to 15%, and PMV, average PMV of between, 0.15 to 0.4. So the percentage of comfort violation hours, so this is like, the number of hours where your PMV actually exceed your predicted mean actually exceeds a plus minus 0.5, also stayed within the 10% range. So in contrast, the model of the R1C1 model show a much larger variation in control performance and a very significant increase in comfort violation hours. So the main reason is because if you look at the plot on the bottom, it's not very visible, but the R1C1 model actually tends to estimate the cooling load in the afternoon. As a result, it tends to be overheated. The space tends to be overheated. So another thing we notice is that, this image on the bottom shows the disaggregation of loads. And what is interesting is that, although both the R3C2 and the R5C3 model were unable to capture the disaggregated heat flows accurately, they were both able to estimate the total cooling load reasonably well, providing further evidence, as to, that, the R3C2 and the R5C3 models would work reasonably well, would be sufficient for this particular use case. So now I'm going to switch gears. So, that kind of like, shows like what we currently have with regards to the model predictive control. And that is still an ongoing study. We are still continuing to test, different cases, including the multi-zone case. And now I'm going to switch gear, and look at retrofit analysis and the effect that, different levels of calibration. So as you collect more data, you spend more effort calibrating the model. And what is that exactly that impact and what it has on your choice of design option, versus, the predictive accuracy of the model. So for this particular, what I'm going to show now, I'm actually taking advantage of an ongoing study, at SinBerBEST, where we are currently carrying out detailed measurements that we have conducted at the Testbed sometime in June. And the objective of this work is actually we are trying to create a high quality data set and energy model so that everyone can benchmark, their algorithms and versions of digital twins in an open and reproducible manner. So although there are many open building data set, there are very few data set, if any, that contains both an energy model and a high quality measurements data. So we are halfway through the calibration process, and I'm going to share, using some of the initial results to look at, if we switch different retrofit options, what exactly is that impact? So for this retrofit evaluation use case, we'll be focusing on parameters related to the building envelope. Specifically, our calibration target would be against hourly indoor dry bulb temperature, which is one of the widely used calibration targets in the field of building energy simulation when we are trying to identify the envelope, thermophysical physical properties. We also employ a manual evidence-based procedural approach to this model development, and we try to keep version controls of the model at each step using GitHub as well as R Markdown. So in an evidence-based approach, the changes to the model are made based on evidence or measurements, rather on an ad hoc basis. So we avoid an automated approach and we select a manual iterative approach because, we really want to track the effects on the model predictive accuracy and credibility and model's credibility each step along the way as we calibrate the model. So the calibration of envelope-related parameters was carried out. So basically, what we did was we turned off the HVAC system, and we run an experiment over 3 days under free-floating conditions. When the system is turned off and the indoor air temperature is allowed to float. So the reason we do that is because we are trying to decouple, the load side model from the system and the plant model. And decoupling the model makes sense because it significantly reduces the number of parameters that you need to think about when you are conducting the calibration. So additionally, right, from our initial review, we found that, material properties as well as infiltration rate are often, the parameters that they try to identify when calibrating against dry bulk temperature. So what we did was we also measure, the thermophysical properties of the building envelope, using RTD and heat flux sensors. And we also try to measure infiltration rate or derive infiltration rate using tracer gas tests. So this slide shows the steps that were taken in the calibration process. So first of all, we built a model according to the as-built drawings as well as the specification without any measured data. And then, we provide the measured exterior conditions as the boundary conditions. And then in level 1, what we do was, we took out the heat flux and RTD sensors to, run the measurements and try to derive the wall and the window U values. And level 2 would be, the tracer gas test to try to derive infiltration rate. And level 3, basically what we did was, we found the floor and ceiling plenum, the boundary conditions were a bit different from what was being modeled. So we actually modeled that in. And lastly, we tuned the convective heat transfer coefficient. So as you can see, a lot of this, the emphasis is placed on the exterior surface heat balance. So this diagram shows the, how the accuracy of the model evolves. And what we can see here is that, at level 0, we have, we see some of the overestimation. It tends to overestimate the indoor temperature during the afternoon. After updating the boundary conditions, interestingly, our root mean square error, reduces to about 0.2 degrees Celsius. And typically in most calibration study, a root mean square error of 0.2 would have been considered extremely good enough. It would be considered good enough, and usually that's where the calibration stopped. But as we went on, right, at level 1 and level 2, we realized, the error actually increased, even though, we are inputting measured data. We derive the U value of the walls and the windows, we measure the infiltration rate and we override it. But interestingly, the error rose to around 1.5 degrees Celsius. And then further investigation revealed that, this was because, the boundary conditions of the floor and ceiling plenum were actually different. So we, again, based on measurements, we input that into the model. And then lastly, including the CHTC, your convective heat transfer coefficient, we managed to reduce the root mean square error back to 0.2 degrees Celsius. However, the question remains, would a more accurate model result in similar decision? So here, instead of looking at prediction accuracy, we decided, why not let's look at, what is the impact on energy performance, if let's say I was to change glazing. So we selected a range of double glaze units from a glazing database. And basically, right, all these glazing units were selected, to try to obtain a range of performance values. So we're trying to get a range, as you can see, of the visible transmittance as well as SCGC. So we try to do a typical design where you place a daylight sensor within the space, and then you test out different glazing units. And then, what exactly are the benefits of using, how can I use my model to basically choose the right glazing unit? And lighting consumption doesn't change, basically because as we step through, level 0 to level 4 calibration, the amount of daylight we receive within the space, does not change because we are changing values, U values as well as infiltration rates. However, we do notice, what we notice is a significant increase in cooling energy. And more importantly, the key observation is that, even though, cooling energy changes, the overall trend, if we look at the last row here, across different glazing type remains the same. So indicating that, telling us that, the models across all calibration levels would inform the same decision. We then try increasing the window wall ratio from 20% to 50%. So like the previous simulation results, the same trend of increasing cooling energy can be observed. However, interestingly, we observe, when you look at glazing A, the result actually changed. So for level 0 to level 2 calibration efforts, glazing A saves energy. So it saves energy compared to the baseline model. But, when we move from level 3 to level 4, it actually consumes more energy than the baseline model. So this indicates that, even, the decision between models at level 0 to 2 might be different from the models at levels 3 and 4. If, let's say I'm considering this particular glazing and it's a decision, should I install this glazing? So I believe such differences would be even more important, for net zero projects and other low energy designs where every kilowatt hour counts. So it is also worth noting that, although the model at level 0 has the same root mean square error, the model at level 4, they could inform the user of a different decision, indicating that predicted accuracy is not always synonymous with model credibility. So these two use cases show that, the choice of the model and the calibration approach should not be decoupled from the intended purpose of the simulation. However, current studies typically only rely on measures of accuracy to determine whether a model is good enough. So current guidelines such as ASHRAE Guideline 14, which a lot of energy modelers refers to, considers a model as being calibrated when the error falls below a certain threshold, as you can see in the table below. There's currently no guidelines on how credibility of energy digital twins for various use cases can be qualified. And this association between model complexity, simulation objective, and the informativeness of the data, this different data stream, is also poorly understood. So I believe these issues are very interesting, and I think they should be explored in future research, if we really want to create energy models that are actually useful digital twins. And with that, I come to the end of my presentation. Thank you.
Thank you so much, Adrian, for a very useful presentation and for keeping us on time. It seems to me, through the presentation by Stefan and by yours, I hope all of us understand that the built environment is very complex and it's not just the subject of throwing numbers at it or doing machine learning models, which of course you're going to hear about in the next presentation. One question for you, Adrian, before I open the floor to other questions. There is a balance between training, that is using data to make the model correct, and using the model. Actually using the model to do useful predictions. You talked a little bit about that, but just some closing thought. How optimistic are you that models of that nature will actually be useful in optimizing the built environment?
I am actually pretty optimistic. Otherwise, I wouldn't be still working in this area. But what I feel is that, the current models that we use, like Energy Plus and even more than Energy Plus, right? They are not designed for operations. So I think we need to tweak them a little bit. And we need to start thinking, more complex models are not always better. More is not always better. And I think we should always think about, how much data do we have? Because, having data would constrain the problem and help you understand the building better.
Indeed. Complex models assume things that you never know, right? And you cannot estimate. Thank you. So let's open it to the folks attending. Please raise your hand or type something on the chat. And I see one hand raised. Sanjeev, go ahead.
All right. Thank you, Adrian, for presenting a detailed study. But looking at your presentation, and people talk about digital twin in different domains. But what I understand from your presentation is your built environment is already too complex. And even if you go for a higher model, not necessarily it will give you the best result. So the question there is not going for a new building to be designed and built and implemented, but the existing building, if I have to do a digital twin, it will be the model that you pick it up depends on what you want to do. And you simplify the model to a larger extent just for that particular, let's say I'm talking about energy consumption. So I just look at it only those parameters, what consumes the energy and how detailed model I should pick it up. And there is no unique answer for it. Is my understanding correct?
Sorry, Prof. Panda, can you repeat the last part? I couldn't hear right.
The last part I was saying is that when you try to build a model for digital twin for a given application, the model has to be designed for that particular application in mind. And you cannot have a generalized model for the built environment that would be equally applicable for different type of purposes. Am I making myself clear?
Yeah, right now, based on what I'm using, so, Energy Plus is a generalized model. I actually think it is pretty hard to try to create a digital twin that will work for all buildings, but then it is designed such that, it is flexible, right? There's different components. But at the same time, I think it would be very nice if we can actually simplify the complexity of this model, which currently there isn't.
Right. Okay.
Thank you. So thank you. We are out of time, but I would like to allow one more question. There is one question on the chat. Maybe you can address it quickly, and I think it relates to the next presentation. And Igor, I know your hand is up. Maybe you can type a quick question in the chat while Adrian is talking. Adrian, go ahead.
Yeah, so I'm not against purely data-driven models. In fact, I do work on those as well. So my view is that, the advantage of the physics-informed model is that, they can extrapolate. So one of the key issues I realize is that, when you work with building operation data, they tend to be very narrow. The building typically operates, the facility manager would just set a supply air temperature of 13 degrees Celsius, and that is all you're going to get. So you don't get that range of data where you can explore. And I think that's where, the energy model comes in. It helps you to understand, as you change, to various operating conditions, what exactly is that impact? And so in my view, I think the white box model can actually be used to actually supplement your black box model. I hope that answers your question.
Yes, indeed, Adrian. I would like, and that is going to be addressed in the next presentation. But before that, I would like us to take a 5-minute stretch break. So 5 minutes on the clock starting now. Adrian, appreciate you staying very late, and appreciate, of course, the next speaker who's staying even later. Both of you from Singapore. So 5 minutes from now, 9:28 California time, we'll resume. Thank you all.